A very powerful technique in solving a circuit is known as nodal analysis. Nodal analysis involves the use of KCL and Ohm's law, and in the future, it'll involve a number of other things that we are learning about different types of elements in a circuit in order to solve circuits. The reason it's so powerful is because any circuit in this course can be solved using nodal analysis. Some of them are simpler to avoid nodal analysis for. However, there are some circuits, and we're going to see one today, that simply cannot be solved using any of the techniques we've developed so far on their own. Let's dive right in and take a look at that circuit. Now, the resistors are all going to be 1 ohm, because I'd like to focus on the technique rather than getting some complicated numbers. And the voltage sources similarly are all 1 volt. One of the major issues with the circuit is that there are no parallel or series connections that we can exploit. Nothing shares current, and nothing shares a voltage. So it looks as though we don't have enough information to solve the circuit. In fact, using nodal analysis, we can solve the circuit. The first thing we're going to do is to label the unknown voltages. Now, you might be saying that there are unknown voltages across every single component. I would agree that that's true. However, there are only 2 that are important, and I'll talk about why. This voltage here, which I'll call VB, and this voltage, VA. Why are these the only 2 that are important? Well, if I know what VA is, then I can solve for the voltage across the 1 ohm resistor here and the 1 ohm resistor here. Why? Because the voltage across this resistor, which I might call VR1, just to make it clear, might be given by, depending on the direction we choose for current, 1 volt, this voltage here, minus VA, this voltage here, all over R1, which in our case is 1 ohm. It's the difference between the 2 nodes that it's attached to. Now, how do we know this voltage? Well, on its own, we don't. What we need to do is decide that one of the nodes is a reference node. There's no particularly convenient place to choose a reference node. So typically, I'm going to choose the one at the very bottom of the circuit. There may be other times when I'm not going to do that, but it's almost always drawn in such a way for this course that the reference node should be at the bottom. Once I know VB and VA, I can again use the exact same procedure to find the voltage across this resistor and this one. If we remember that everything along this node is at the same voltage, then this is also VB. So once I know VB, I know this is 1 volt with respect to the reference, I also will know the voltage across that 1 ohm resistor. So, one of the key steps is recognizing which voltages are actually unknown. Typically, these are nodal voltages, here and here. This voltage is also a nodal voltage, but we knew what it was. It's 1 volt. And so we only really had 2. Now that we've set up our circuit, this would be called the setup step. It involves identifying the voltages and currents. But we're not done yet. What we need to do is actually find what they are. What I very strongly recommend that you do is try to find an expression for the current through every single component first, and then combine them using KCL. I'll demonstrate what I mean. I'm going to choose directions, and I'm going to label my currents. We're going to have quite a few of them. And what's going to happen is we're going to develop a series of equations that we can solve simultaneously. So I have developed I1, I2, I3, I4, and I5. I get 1 current per branch. Now, many times there are shortcuts where we can use KCL and Ohm's law together all at once. In the beginning, I don't recommend doing this. So what I'm going to do is develop equations for each of these currents and then combine them. I1 is going to be given, notice the direction I chose was this way, so it's going to be 1 volt minus VA over R1, which is 1 ohm, which gives me 1 minus VA. Similarly, just make sure I can organize my page here, I2 is VA minus the reference voltage, which is 0, over 1. I3, I've chosen it going this way, is VA minus VB over, again, 1 ohm. I4 is VB minus the reference, 0, over 1. And finally, I5 is VB minus 1 volt, remember I'm going this way, over 1 ohm. Now that I have these expressions, I can start to combine them using KCL. So, by KCL, I1 flowing into the node has to equal to the sum I2 plus I3. Similarly, I had that I3 is equal to the sum I4 plus I5. This is now using KCL. I'm going to substitute these now into equations using the unknown nodal voltages. Why am I doing that? Well, here I have 2 equations, but 5 unknowns. I can't solve for this. However, looking at this set of equations here, notice how all of my unknown currents are actually in terms of only 2 unknown nodal variables, VB and VA. So what I'm going to do is rewrite these 2 equations in terms of only those 2 variables. All I'm going to do is directly take the equations I developed and plug them directly in. We're going to simplify later. So, equation 1, 1 minus VA is equal to VA plus, there we go, VA minus VB. Equation 2, VA minus VB is equal to VB plus VB minus 1. To simplify this a little bit, equation 1 really tells us that 3VA is equal to VB plus 1, which implies that VB, which should be a V, is equal to 3VA minus 1. I can now substitute this into this equation, so all I'm really doing here is solving my simultaneous linear equations. And when I do that, eventually what I'm going to end up with is that VA is equal to 1/2 of a volt, and similarly VB is equal to 1/2 of a volt. In this case, they happen to end up the same. So, now that I know my unknown voltages, I could go back to these equations here and solve every single unknown current. I'm going to leave that to you. Let's review the steps though, because they are important, and if you follow these steps, you'll do quite well. Step 1 is setup. Here you identify the node voltages that you need to know. Step 2 is equations. I'll use the shorthand EQ'(NS) for equations. This involves writing currents equations in terms of node voltages. Remember, we're going to have far too many currents to work with, but we're not going to have too many node voltages. Step 3. KCl. Combine these using KCl. Step 4, solve. What's very important in this course is that no matter what we do, we'll always have n equations and n unknowns. Those unknowns are going to be the unknown nodal voltages. Those equations are going to come from KCl. The equations are also always going to be linear equations, which means we can always solve them. As you progress through circuits, you might learn about elements that are nonlinear. Nonlinear elements unfortunately can't be solved in a nice way. However, the very large majority of circuit elements that most people encounter are going to have linear properties. So as long as you remember our 4 steps, you can solve most of the equations in this course. In the next video, we're going to talk about a special case. We'll see that there's an additional step we're going to have to take to handle this special case. But luckily, there is actually only one such special case. As long as we can remember how to apply it, we can solve all of the circuits in this course using nodal analysis.